Let's start. Yeah, we're good to go.
All right. So just like Kelechi said, we'll just go straight into it, and without taking too much of our time, I'm privileged to welcome everyone here to the fourth in our series of system dynamics training for beginners. We've had a couple, and the link will be shared again for those that missed out on those sessions to join or to play back and catch up on what we've done so far. So for today, we'll be having the privilege of Professor Titus Olaniyi taking us through system dynamics resource management for beginners. I hope we can all hear me though. Can we all hear me?
Yeah, yes.
Okay, fantastic. All right, so Professor Titus Kehinde Olaniyi is a professor of sustainable energy planning and management. He leads the Sustainable Energy and Allied Disciplines Research Group at Glasgow Caledonian University, London. He's an academic, and he was the academic lead engineering, environmental, and sustainability at GCUL. He was the deputy provost at Afe Babalola University at Ekiti. He's a decision scientist, a registered engineer, a senior fellow of Higher Education Academy, a senior member of the American Institute of Aeronautics and Astronautics. He's also a chartered information technology professional. He bagged his PhD from London South Bank University in decision support systems for sustainable energy planning in a developing economy. His MSc was in energy engineering, while his BSc is in aeronautical engineering. He has taught widely across diverse disciplines. He is a Nigerian, from what I see here. He has also served as a member of Aerospace and Defense Sector Strategy Group, formerly a scholar at the Air Force Institute of Technology, Kaduna. He adopts systems thinking, system dynamics as well as a sustainable decision support tool for planning and policy formulation. His teaching and research and consultancy services include energy, aerospace, information communication technology, and systems. Let me just pause there. Without further ado, let's make welcome Professor Titus Kehinde Olaniyi as he takes us through another series of system dynamics for beginners. Thank you.
Okay. Thanks very much, Dr. Falebita. Anytime I hear this, I just wonder, who is this? Whom are they talking about? And the things that comes to me, I just use that opportunity to thank God Almighty, and also to thank all those friends and colleagues and families, including students who has worked with me over many years, and also to be able to be where we are at the moment. I also want to thank everybody on the platform, those who have taken an advantage, those who have taken the opportunity to join us this afternoon, and also to thank those that I thought would be coming, and anyone who will be listening to this who are not able to make it today, who will be listening to this. And I take this opportunity also to bring a very solid welcome from my team in London, both from academics and staff, and also to wish Nigeria and our Muslim faithful a happy Eid celebrations. And I think before much ado, I think it's also important for us to just go through what we wanted to go through today. System thinking, system dynamics, has been said, is something that I come across by accident. How did I come across it? I just give you a very short intro to that. I do understand that a lot of us come across it in one way or the other. I came across system thinking, or system dynamics as we call it, during the course of my PhD. At the time, I was looking for tools and techniques to address the dynamics and the complex relationship in respect of energy planning, particularly in the global south, what we refer to today as global south, but in the developing country, but what we now talk about as the global south. I was looking for tools to address that. And I saw a lot of tools as an engineer, a lot of mathematical tools. And the thought in my head at the time is that, how do I make this how do I make this tool something that energy planners can think of? At the time in Nigeria, the minister for power was a lawyer, and I guess to myself, using this mathematical equation, Laplace transform, high-level differential calculus, I guess no lawyers will want to listen to me. So I was looking for tools and techniques that can address this complex relationship in a very simplistic form. Therefore, I came across system thinking as a tool. So that's how I came across it. And I'm sure if I continue to ask people here, everyone will have different reasons how they came across it. But without much ado, let me just go back to this exercise, and I think I will be in and out. And also, please, if you want to put your camera on, there's no, we don't have anything against it. We want to hear from you. This is not my session. This is your session. I just want you to be able to sort of make absolute contribution to what we are hearing. And let me also mention that there's no means that 1 hour will be enough to be able to pick up everything that is needed, or 1 hour, 15 minutes will not be enough. So what we're giving here, I will be jumping from point to point for us to be able to get to where we are. But I would want to hear from you. I would not want to talk for 30 minutes without hearing any voice, or 1 hour without hearing any voice. Has anyone here has gone through this pre-reading at all? At all. I'm not thinking about those who are setting it up, but I also want to thank those who have set this up. I'm talking to Dr. Falebita, I'm talking to Kelechi, I'm also talking to others who have also spoken with me, including my very good friend and brother, Dr. Bilo. Hopefully, I'm not sure, maybe he's not able to join us here, but I'm sure we will get to hear about this later. So has anyone taken any time to just go through this pre-reading? And what does it say to us in terms of what is the issue that is there? What can we remember? I don't want to talk about the whole lot, but I just want to ask about, have we taken attempts to look at this reading? Anyone? Put your microphone on and speak. Anyone who have taken, who has looked through this one-page document? Put your mic on and speak, please. Anyone? I'm relaxed. I have water with me. I have coffee with me. I also want other people to also have the same thing as well. Has anyone gone through the pre-reading at all? Anyone? Nkechi, you are here?
Yes, Prof, I'm here.
Yeah, hello.
Okay, that's right. So in one line or in one sentence, what do you think the pre-reading is actually addressing?
It's talking about the issue of energy resourcing, resource planning, and how fossil fuel and renewable energy as sources of energy can be brought into energy planning.
So thank you very much. And I think we can see here. Thank you very much, Nkechi, for that contribution. Any other person who wants to speak to say something?
Hello.
Go ahead, sir.
Sorry? Yeah.
Sorry, go ahead.
Sorry. Really, I went through the manuscript and I was like caught up in a dilemma between two Greek devils, like telling me, okay, we need to transit to clean cooking. To clean fuels. While we are doing this, there's a log behind from the fossil fuel demand, from the fossil fuel aspect, whereby our transitioning might not really be smooth. We need to go back to the baseline, which is the fossil fuel, go back and forth, So there was a contradiction in my mind, so I just had to just leave it.
That's right.
Yeah.
Okay, thank you very much. So the dilemma before, so when you do system thinking or system consultancy, this is the way you speak. Managing director will sit down in an aircraft, will listen to or go to a meeting, and then during the course of the meeting, he'll be standing up, having his water or orange juice. Somebody will mention something to him or her, and then they will just think, oh, this is a very good idea. I think we can do this and do that. So in a finite world, it is always not possible to have everything at your fingertips. So you've got to make sacrifice. So the discussion here is about we are talking about an organization who has a fixed capacity in terms of their production output. There's a limit to how much you can produce. If you hear the story of what's going on in Nigeria now, I mean, if you look at the past government, I want to make an assumption. I'm talking to a lot of people who have some connections with Nigeria. If you don't, my apology. There have been times that people have been talking about during the previous government. There were discussions about, oh, let us produce 10,000 megawatts. You were hearing that, oh, let's produce energy of 10,000 megawatts. But there are other discussions at the back end to say, yes, this is a very good vision for the government, but our transmission capacity cannot be more than 4,000 megawatts. So we are locked up. The government, this is exactly what the government wants, but this is what our capacity is. Exergy Vision is in this, it's also in this particular position. Exergy Vision, according to what the brief here has talked about, is talked about the fact that this particular company have two dilemmas. The first set of dilemma is the fact that they want to produce renewable energy and they also want to produce fossil fuel. But there's a contradiction. If you look at exactly what I've given here, the senior management team have directed that there must be a priority for fossil fuel just because of the issue of energy transition. There must be a priority for fossil fuel. And I'm sure those of us that are here knows very well there is a limitation, there's a dynamics to exactly what we could do as far as this fossil fuel is concerned. And I think I'm also going to get one or two of us. It's not a very big read. We just get a very short read and we'll move into what the system thinking personal diagram should look like as a result of what we have read. I just want a volunteer who can see the screen to just give us this read again, just to get a grip of what it is, because if you don't have an understanding of what the briefs are, it is always very difficult sometimes to draw a causal diagram. Of course, like Sherry have said, there is going to be some contradiction of it all in terms of what we can do, what we cannot do. Can anybody just help me in terms of reading it out? Let's hear it quickly.
Can I go?
Go ahead, sir.
I should read your manuscript, right?
Yeah, just read. It's just a page.
Okay.
Just read. As you are reading it, I'll be stopping you from time to time, and I will just be making some explanation. I will go straight into the system thinking. I will go into the system dynamics.
All right. Resource planning and management.
Okay.
Irony of limited constraints.
Yeah.
Energy Vision International produces renewable energy and fossil fuel.
Okay.
The latter coming from an order waiting list as the senior manager team at EVI has clearly directed renewable energy to be given a priority, given their international commitment to sustainable obligations.
Yes,
This
so that is not,
implies-
sorry, 1 second. That is not in doubt. We know very well now that the issue of sustainable development is not a myth. It's not a myth anymore. Everybody is adopting to it. Everybody has moved into it, and it's got to be done. Go ahead, sir.
This implies production of fossil fuel will only occur after renewable energy obligations have been met.
Okay, so the question is, sorry, 1 second. Every time there is something into the production facility, remember our production facility is limited. Every time there is an order coming into the production facility, we must give priority to renewable energy because that is the international obligation. Let's go ahead, sir.
For simplicity, it can be assumed that unmet production of renewable energy will be taken by other market operators.
Okay.
Although,
So if we don't do the renewable energy, other operators will take it. In some instances, you pay penalty for not being able to meet that obligation. We don't know what they've been given to the management team. We do not know what indirect subsidy has been given to the management team, but Exergy Vision senior management team has agreed that we will take over the renewable energy. We'll give them priority every time they come through our door. Let's go.
although these adds huge penalties to Energy Vision International and such, the senior management team would not wish to see this happening, even though it is unavoidable given real-world practicalities and constraints, which include production capacity, availability of personnel, etc.
Thank you.
Given the extensive experience of market demand, the production team at EVI have a predictive demand for fossil fuel, and analysis of past forecasts show that 20 kilowatts capacity per week on the average of three per day is added to the order waiting list.
Okay,
The production manager.
Okay, I just want us to look at it. Every Monday, for example, we get an order of 20 kilowatts of fossil fuel to be produced. Experience have shown us in this particular case. Okay.
The production manager is notified of these additional requirements to the waiting list once per week, typically on Monday morning at or before 9:30, although production could commence on any day of the week.
Okay.
Ironically, and by its inherent nature, demand for renewable energy production is much more valuable. Analysis in the past 5 years have shown that on any day, the demand for renewable energy production can be presented by normal distribution with a mean value of 4 kilowatts and standard deviation of 2 kilowatts. Although the length of production, which means the time it takes to complete production, is slightly variable. It seems reasonable to assume that production of renewable energy takes 5 days. At the end of this period, they may be transferred to an outsourced logistic company before dispatched to the end user. Production of fossil fuel tends to take 3 days in the production units. As a reminder, the production priority policy issued by the XMT at EVI reads, all renewable energy must be allowed in the production units, and any spare capacity are then used for fossil fuel production.
Thank you. Thank you very much. I think we have gotten to where we want to move now and slide into what it is. So the first question there is this: what should be a reasonable production capacity at EVI that meets the demand for renewable energy and fossil fuel? Let us work in terms of days. So it takes from the order we're getting. Is that correct? Let's just talk about renewable energy, which is important to us. It takes 5 days. Is that correct? Okay, sorry. Let us start from the order we are working on. Let's just go to the order we're working on in terms of, so that we'll be able to find out precisely what it is. So what do we take first? Let's take the average time to produce fossil fuel, as can be seen from here, is 3 days per week. And then it takes 3 days. First, it takes 3 days to produce. So when you multiply 3 by 3, you have 9. So we need a production capacity of 9 kilowatts. Is that correct? In it. But in the case of renewable energy, it takes an average. So we can see here, it's where we talked about, it takes an average of 5 days a week. And then from what we're getting here, we're getting 4 kilowatts. And then if you multiply 5 by 4, you take 20. So 20 plus 9 is 29. So that is how we get this 29 kilowatts. So that is the average capacity per week. Very straightforward from what is discussed here. Any clarification on that? Any clarifications on that? So question number 1 is about 29.30 per week. So if you finish that, let us just go and talk about the second question said, what would the Coastal Loop diagrams look like? I don't know if any of you have put an attempt to do this, but to draw the Coastal Loop, this is the approach I take. I tend to use Venson to draw Coastal Loop and use Stella to draw the stock and flow. System dynamic is not complete without a Coastal Loop. And I've seen people just chop, going through from the descriptions into stock and flow. I think it's wrong. I think it shouldn't be done. position is that draw the stock and flow first and then move into, sorry, do the causal loop diagram first and then move into stock and flow diagram. So this causal loop diagram we came across looks like this. Is this small enough, or you want me to show it in PowerPoint? Is it visible enough, or do you want me to show it in PowerPoint? Okay, Sherry, go ahead.
Yeah, thank you, Prof. I have two questions. Sorry for cutting in.
Okay.
First and foremost, you said you use Vensim for CLD, which is a causal loop diagram,
Yes.
and stock and flow for Stellar. Why this? Why not just stick with one? And secondly, on the issue of causal loop and stock and flow diagram, most of the time when I draw a causal loop and I try to translate the causal loop into stock and flow, I realize at a point I might not be able to consider all agents or probably all the variables in that causal loop.
Yes,
in my stock and flow, which might limit my comprehension. So do you think it's now allowed, or it would be a nice approach to work, reframing my causal loop because I was limited by my intuition of the stock and flow? What are your thoughts, sir?
Okay, let's go to the first question. The first question is just the questions of just the timeline that I've gone through. At the time I started my PhD, that's when I came across system thinking, system dynamics. The interface with drawing stock and flow with Vensim was not as beautiful as what it looks like these days. I think all the models has improved. At the time, I had an option either for the university to buy Stellar at the time, Vensim or PowerSim. The discussions at the time was in early 2000 was to go for Stellar. So I started using Stellar for drawing. I started using Stellar to do my stock and flow diagrams. But at the time, the Vensim was free, and this Vensim version that we're looking at is being using for education purposes, and I like it, and it's very, very nice. And if you do at the time, Stellar will not allow you to draw stock and flow at the time. The latest versions will allow you to do it, but I still prefer the Vensim. The Vensim one is very neat and it's very clean, and I think they've perfected the way it is, and it's always been very useful to use. And there's a free version you can use, and that is just a choice that I've taken. And so I use for causal loop diagrams, I use Vensim, and for stock and flow diagram, I use Stellar. So it's just a question of the way I've gone through, and I've not seen anything otherwise. So that was just a choice. Yes, on your second questions, in the sense that, okay, what do you draw? What do you go for? Part of the way of checking your system thinking, your stock and flow and causal loop diagram, your stock and flow must replicate your causal loop diagrams. If it doesn't represent it, then it is not a full fit. But there are instances that you may not have to get to the stock and flow. From a professional point of view, as a consultant, sometimes you end up the work at the causal loop level. You may not necessarily have to go into stock and flow. By the time you start going to stock and flow, you're looking at equations, you're looking at mathematics. Your decision maker might not be able to take it. But the question here is that we can look at these causal loop diagrams and talk about it and discuss it and find out precisely that the problem actually lies in the causal loop diagram. Most problems can be resolved at the causal loop level. Most dynamic problems can be resolved at the causal loop level without necessarily going into stock and flow diagram. So this has been the notation. But again, let me come back to this and see exactly what we have in front of us here. And I want us to take a few minutes up until about 1535, 1540 to look through these causal loop diagrams. And let's try and get a feel of it. Getting a feel for it, what I want to ask you first and foremost is to look at the variables that are represented in here. And I will be switching in and out to also look at the stock and flow diagram and also run it. And I think everyone can pick up anything that you want to talk about here for clarification, if you wish to. Okay, I use a convention in drawing Kosaluk diagram. Again, this is a convention I picked up from early 2000 that I use. If I see a flow, I use all small letters. Anything you see on the stock and flow diagram, sorry, anything you see on the Kosaluk diagram that has all small letters is a flow. Anything you see that has first letter capital is a stop. Anything that you see that has all capital letter is a constant, or it has nothing, no input coming into it. Anything that are used as converter, a converter that adds an input and output, the first two letters is capital. I repeat, all flows. Flows are rates. Anywhere you see me, anywhere you see displaying a flow, it is all small letters. Anywhere you see all capital, first letter capital, the rest of it small letter, just first letter of every word capital is a stop. Anywhere you see demonstrating two first letter capital, it's a converter that has an input and that has also an output. It's an information flow. So we can talk about information flow and physical flow. There are information flow, there are physical flow. So a stock and a flow, that's exactly where the name, use of the word stock and flow diagram comes into being. I can show this and I can be flipping between this and this stellar so that we can see the difference between what is going on. But I'm happy for us to discuss this. Like I said to you, in many cases, this is what you need to show to the decision maker. And you understand? I mean, if we're in a class environment, we will draw this ourselves, we'll go into the basics and then try and put our hands on it and draw it up. And then for me, once I have this, I'm able to move. And I'm also happy to take any particular variable and let us have a discussion on it. So basically, what we have here in this diagram here is that based on what Shari mentioned, Babajide mentioned earlier on, is we have the renewable energy production here in green. We have the fossil fuel production in red. Fossil fuel will not produce unless it gets information about renewable energy. I'll do a very quick click. This is the stock and flow diagram. I can work backward and also work forward. So basically, look at the stock here. I'll do this and I'll go back and I'll come back here again. If you look at the stock here, this is total stock that is being produced. But can somebody tell me what are the variables that goes into the total stock? You see what variables are actually adding to the total energy stock. The energy can be either renewable or fossil fuel based. Can anybody tell me what are the inflow into the energy stock?
Yeah.
Let's go.
Yeah, the picture inflow, the renewable energy production.
Okay, so there's renewable energy production is going in there.
Production.
There's fossil fuel production going in there. Is any other energy going in there apart from those two?
The fossil productions.
Which one? Fossil fuel production. Fossil fuel production is going in. Renewable energy is going in. Is that correct?
Yeah.
No other variable, no other energy is going in. From the brief that we read, we had that two side of energy is going in, fossil fuel and renewable energy. So that That is a validation that from what the owner of the problem has described to our coastal loop diagrams, to our stock and flow diagram, that information is correct. So let's go to the coastal loop diagram and see what does the coastal loop diagram looks like. So look at the, okay, so before we go to the coastal loop diagram, if you look at it, what is going out of the energy stock? What is going out of dispatches? So dispatches comes out of the energy stock. So production can be either renewable or non-renewable, but once they are produced, irrespective of what energy source is being produced, this energy source must leave the production center and go out as dispatches. So it's got to leave the stock. So if you go to the coastal loop diagram, you can see the energy stock. How many variables is going into the energy stock? How many variables? So the green, the blue line is what is going in. What is, so when you see the red, can you see the red? So the blue line, so you can see this plus here, renewable energy production goes into energy stock, fossil fuel production goes into energy stock. Does any other energy goes into energy stock from this causal loop diagram? No. The only other thing that goes, that has anything into the energy stock is dispatches. Dispatches take away from it. This take into it, this take into it. But this information, available production capacity, is not taken away from it. It's just an information. Just an information that is being fed into it. See that? So this is how you validate your model. If your causal loop diagram does not replicate your stock and flow diagram, then that story is incomplete. And this scale is a very, very easy thing to pick up. I wish I'm with you. We can put our hands on the system and begin to draw, because we have only 1 hour. So that's why we got to put this together. So as you can see that the relationship between the stock and flow, it's that information is very important. And this model is not all and all, but it's captured every other variable that we needed to know. Any questions on this? Let's take another variable from the stock and flow.
Yes, Prof.
Go ahead, sir.
Please, on the CLD diagram.
Okay.
Yep. The energy stock and the dispatch. I was thinking this red flow moving from the stock to from the dispatch to the stock. I was thinking it should be the other way around, like the stock to the dispatch, something like that.
Okay. In drawing stock and flow or causal loop diagram, because the question you have to think about is this: where is the force coming from? That's the way to perceive it. So we have an energy stock. The force that is bringing the renewable energy into the system is from outside. Does that make sense?
Okay.
Does it make sense? The force that is pushing energy, that is increasing energy stock, that either be renewable energy or be fossil fuel, that pressure is from outside. It's got to be produced before it goes into this warehouse. Does it make sense?
Yes. Yes.
But if you want to dispatch, the ability to dispatch depends on exactly what you have in the stock. It's just like money in your bank. So the money in your bank, to be able to withdraw the money in your bank, there must be money there already.
Okay.
But if you want to pay into your bank, either through salary or through transfer, the force to put money into your bank must come from an outside. So what this is saying to us here is that the force is coming from an outside, but in this case, it is negative. The force is coming from an inside. So let's take an example. When energy stock is zero, what can dispatch the 1 or 2? No.
Zero.
Yes.
Yes.
But if energy stock is zero, renewable energy production can still increase. So when you draw the causal loop diagrams, this is the way you represent it. For anything that is adding to it, you get the arrow into it. For anything that is taken away from it, you get the arrow out of it. So when you are drawing the causal loop diagram for this one here, I just give an example here. Let's put this here. So if I want to add anything into this, do the flow, I move from outside to inside. Sorry, I took the wrong thing. So if I want to add anything to this stock one, I've got to come from outside to inside. So it's moved onto it now. So if I move this anywhere, it will run around with it. Is that okay? So that is how I will have drawn the renewable energy production and fossil fuel production. I will have moved something from outside to inside. But if I want to take something from inside the stock, such as dispatches, I will have to take a flow. So I cannot start from outside. I have to start from inside. It's where the force is taking place. So outside. So to draw these dispatches, I did that. If I want to add one more thing that goes in, I will have to do this from inside to outside. So, but if the force, it didn't take this one, let's see. Second. From outside to inside. So that's where it goes. And if it's a biflow, if the flow is allowed to go in and go out, then I will use a biflow. But that's not what we're discussing here. We're making an assumption here that once the goods is dispatched, it doesn't come back. But if you're going to be modeling this based on the fact that these goods can go out and it can be rejected and it can come back, then in that case, we do a biflow. And then that's a different story. Then we have to represent that accordingly. Any other question on that? Any other question? So the same way, I just also want to tell you about few things that we needed to discuss. Basically, the unmet demand. I want to mention something about this unmet demand here. You know, there was an instruction that if we don't, from the brief, if we don't fulfill the obligation, the penalty will be paid. Is that correct?
Mm-hmm.
Yes. So if you don't fulfill the obligation, the penalty will be paid. So we do not wish to see this happening. A variable real world and constraint. So we talked about here simplicity. So you assume that unmet production will be taken by other market competitors. We don't want that because there is a penalty for doing that. If you're allowed to go out, you might not come. That customer might be more happier there. You may never come back again. So you try as much as possible to avoid that. But in some cases, very difficult to do. So if you go back again, into the model and see exactly this is what we have here. We're going to start running the next 5 minutes, but we'll run the model. But I just want us to be comfortable that we can see that the causal loop diagram is a direct replica of the stock and flow diagram. And everything here, things like, I don't know, maybe we can give a shout also. What is going out of dispatch? So what is going out of dispatch is the production type. So this dispatch is here, so intelligent that it knows when a dispatch goes in, he knows how long it should take. We said the dispatch will take 5, is that correct? 5 working days to do. So if you click on the dispatch here, we've said 5 and it is 5 on the model. In this case here, we said 3 and it is 3. So the model is a true replica of the system. Any question? But like I said to you, from a professional settings point of view, basically what you usually show when you are with the client is this cost value diagram. And there's a lot of strength in the cost value diagrams. There's a lot of knowledge that we can deduce from this. Because if we even start talking about this cost value diagram, when we do a teaching of these natures, we don't allow students to move on until they have a clear understanding of the cost value diagram. And like I said, the way we've drawn the cost value diagram is anywhere we identify a stock. And when you identify a flow, is everybody clear about the difference between a stock and a flow? And how do we identify if it's a stock, if it's a flow? Is there clarity on that? Stock and flow? Any questions on that? Okay, I think I can everybody says it's okay, but you've done 4 sessions on this, so I mean, I thought of that as well. This group are so advanced. I wouldn't want to hear what is different between the stock and the flow. Any issues in terms of the drawing? And for some of you that are here, the Vensim is free. You can always look at it and download it. I have few PhD students that are doing their PhD, and they're not going to stock and flow. They're finishing their PhD just with this, just with the cost value diagram. It is not mandatory that you should draw the stock and flow diagram, as long as they were able to sort of finish this, and that is it. Any issues in terms of how to draw this? Any issue in terms of how to use this tool? Very straightforward. You only need 5 minutes to learn it. If you just work with somebody who knows how to use it, very simple to learn, very simple to pick up. And from there, we went on to look at the stock and flow diagram. I'm not sure is anyone working at the background and having issues that want to share their screen so that we can take you through? I don't mind. If you're working on the background, we want us to give you the permission to see what you have at the back end, and we can talk you through how we did it or how to do it. There are a couple of assumptions that were made. So in this model, I will just, if I click on it, in this model here, we can start from the stock. So the original stock that we have was 0. So if you click on the stock, the original stock we assume at the beginning of it was 0. In the case of unmet, also all the stock was recorded at 0 at the beginning. Is that correct? The time to produce renewable energy, we saw it in the brief, it was 5. So when we look at this, we click on it, it shows 5. For fossil fuel, it says 3. We put 3 there. If you want to change it from 3 to 5, 5. If you want to do this, it changes average of 3 to 5. We can also put that there. If you allow, the model will allow us to do that. But there are instances where we have made some changes. So I want us to look at maybe one or two of the variable. Let's just look at one or two of the variable. So if you look at the unmet renewable energy production, the unmet renewable energy production, I just wanted to have it talk on this. It is renewable energy minus renewable energy production. So the total renewable energy that is coming minus whatever that is being produced. That is what it goes in here. But this unmet renewable energy is the penalty we pay that we talked about earlier on. And I've run the model a couple of times. We'll run it again.
Hello, Prof.
Go ahead.
Yes, so there's a question in the chat box.
Okay.
So you might want to take that.
Okay.
It's asking if it's for a social science-based research.
Okay, Shadi has asked the questions that replying to. I don't hear any voice. Oh, that is sad.
Yes,
Can you hear me now?
I was asking that the student, your student that was working on CLD only for a research, is it kind of social science-based research?
Yes, it could be social science. Actually, what happened is the nature of the problem you want to explain. If the focus of your research is to enable a better understanding of the interactions and the complexities of the model, i.e., by having something such as this, in terms of your analysis, if this is what you are interested in, you want to see how various interactions are interacted with each other, and then I think it's more important to use the closed loop diagrams as a way of explaining what the problem is. I mean, it ends there. It ends there. Once this, but basically, I mean, if you look at it from this point of view here, and what you need to be looking at for is to look at the leverage point. The leverage point is looked at. So the leverage point, sometimes you'll be looking at is the constant, the exogenous variables. The one with full capital is the one to look at for. What are how many ones there are with the full capital?
Yeah.
Tell me what are the things there with full capital? All letters capital. Four. So can we name them?
EFV total production capacity, renewable energy, fossil fuel production time, renewable energy production time.
That's right. So if we change that exogenous variable, we can change the behavior of the model. So it is nice, universities want to recruit many students, but if you don't have a capacity, if you don't have where to put them, what do? You get the money in the short term, students complain, and you lose them, and lose them for many years. And be penalized for taking too many students you can't do. So same thing also with this particular problem we're looking at. Yes, it's a good idea that we want to be able to fulfill all righteousness with fossil fuel, with renewable energy. But our ability to be able to do what we want to do also depend on the capacity that we have. If our capacity goes down, we'll not be able to meet this model. Our capacity, like we said in the initial one, it is EVI is total production. So let me just take a typical example. So we agree that the total capacity is 30, is that correct? If the total production capacity is 20, so call another graph again. We're not talking about how do you design these and so on and so forth. We're not selling any model or any software here, but we just want to see what we can do with it. So we'll So we'll look at exactly some of the variables we want to measure. So we'll just add a few one into it. So let's just take the one energy stock, for example, how much we produce. So that is there. And then we want to pick up maybe the total of met renewable energy, for example. Because that's what we're paying, that's the one we're paying penalty on. Met renewable production. So let's take the met renewable production over time. So these are the two we're measuring. So if you run this model, just go back again. Let us just assume. So you can see now the energy in the stock varies between 20, 15, 20, and 30. Let's just take, for example, we put 30 here before. There's something wrong with the plant, and we put it as 0. What do you think will happen with this model?
It will collapse.
Collapse. So let's run it. Look at the net production, see how big it is, and look at the energy in stock. You see 0 at the bottom, so 0. This is what has happened with the model. It's a lot of things we can do with the model, but just to give you an idea of what is going on, you can see on met production is going very high, and the energy in stock, this is where it is. And what happened if we change the production capacity times 3? Running from 0 to 90. Is it wise? Let me ask you, is it a wise thing to do? Will you support your line manager to increase this from 30 we calculated to 90? Is that a good idea? Let's hear from people. Is it a good idea? So you, as the system thinker, and you are advising the government, you are advising not the government, you are advising EVI senior management team, maybe the director, and he says, well, somebody came in, just coming from, I don't know, study so many things, BSc anywhere, PhD everywhere, and they said, okay, let's increase the capacity to 90. You agree to it. And if you run it with that model, you see what you have. You have a production capacity of 90, but your optimum output at any point in time is not, it's maximum of 30, maximum of 30. Can you see that? It doesn't matter what you do. You can increase your capacity to 300, nothing will change. Nothing will change. So that's why some organizations kill themselves by just increasing their capacity, but without market for it. So if you want to increase your total output, what do you think we need to do? What needs to be done? What would you do? Let's go. Let's hear from you. What would you do?
Consider the renewable production time and
Time. So if you want to reduce the time to produce renewable energy,
yes.
so what do you want to do to that time? So under this scenario, the numbers ranges from, we're just looking at the numbers at the bottom. Okay. So what would you want to raise it to? You want to reduce it or you want to increase it?
Reduce the time of production.
It is 5 or here. So you want to put it to what?
2, let's say 2.
Okay, what impact would that, what impact would that have on your renewable, on your fossil fuel production?
It would make the fossil fuel dispatch later,
Okay,
while renewable energy dispatching much earlier.
okay. So on this graph also, we can show that, do another graph and show that we can do a comparative analysis. I mean, that's not what we're doing today, but it's one way of looking at it. But what we are showing here is energy in stock. This energy in stock is not differentiating between renewable energy and the other one. It's just looking at this, but we can go here and remove this. And then we can look at, let's remove this. Let's add renewable energy. If you want to look at renewable energy production as a flow and the fossil fuel production. Not right. Yes. What did you get? So the production in terms, so here we can see the difference between the renewable energy and the fossil fuel energy productions. And somebody asked me how. So basically, if you want to threaten your decision maker, if you want to threaten the policy maker, you show them a graph like this, then they're in trouble. So when you have something like this, what do you think will happen? Is this is the practicalities of life? But does it give them sleepless nights? It does.
It does fluctuations.
Yes, it's a lot of fluctuation. It gives them a lot of sleepless night. The question now, the question for all of us is this: how do I minimize this? That's the question for us. And we have run this.
Maybe we consider containment or storage.
Yes, we can do. Yes, that's one of the areas of looking at it. But the question also, I think the question we ask in practicality is that you can only produce within your production capacity. There must be another exogenous variables that push it. Otherwise, you will not be able to. For these organizations now, whatever the case may be, because of the way the order is coming in and because of dynamics in this process here is the order. So let's just looking at the way you remember in the brief that we read, and we read that brief. So basically, most of the problems in this model is coming from this paragraph. And somebody read it again for us from that one I highlighted.
Ironically,
Okay.
and by the inherent nature.
Ironically. It's fine.
Right. Okay. Ironically, and by its inherent nature, demand for renewable energy production is much more variable. Analysis in the past 5 years showed that on any day, the demand for renewable energy production can be represented by a normal distribution with mean value of 4 kilowatts and standard deviation of 2 kilowatts.
So basically, that in itself is a noise into the system. When you have a production, so what that means to us is this, that the order of renewable energy, it's in itself a mess. Somebody comes for renewable energy, with the average we've been getting is 4. But sometimes they bring 4, sometimes it's 5, sometimes it's 6. You remember 2 plus or minus 2. So 4 plus 2 is 6, 4 minus 2 is 2. So the order can be, the order for renewable energy, sometimes it is 2, sometimes it is 3, sometimes it is 4, sometimes it is 5, sometimes it is 6. How do you plan for 5 different scenarios? So the fact that the order is coming the order is coming in a way that is distributed among the main, it makes life very difficult. If I make the standard deviations 3, do you think the noise will be more? Yes. Yes. Can we make the standard deviations 0?
Better.
If we make the standard deviations 0, second,
Maybe fossil fuel. I said maybe fossil fuel.
fossil fuel. No, I think our focus is on renewable energy. Whatever we produce in fossil fuel, we are happy. The management is not upset about fossil fuel. On this occasion, it is not the fossil fuel that is causing the problem, because the fossil fuel, the model is constructed in such a way that anytime we get order for renewable energy, fossil fuel will be stopped. And the discussions about fossil fuel, we only get it once a week. We get an order once a week, and so we've made that easy for the system. Don't give us renewable energy order every day, but bring it once a week. That is the contract we had. And once a week, 20 kilowatts, not more than that.
Can I present maybe a solution?
Okay, let's hear from you.
So I was thinking that if they had a contract with their with the others to say that this is the amount that we want to make an order for every week, so that the order is variable. They have specific clients and the minimum order that must come in. Maybe that would.
Okay, so what will you do in that condition? Because what is done here is that we get order of about 4 kilowatts per week. But you remember, renewable energy is also a very, it's not a stable one all the time. So, I mean, I just want you to repeat what you said you want to do. You want to do a contract and say to them what?
Okay, so what if there's a contract that says that the minimum order of renewable energy that can be made by any client will be 4 kilowatts, nothing more, nothing
less.
Stable.
Yes.
Yes, it's a stable.
Yes, if you do that, so the standard deviation will become 0.
Yes.
Yes, if you do that, yes, we'll get a straight line. But is that possible in practice?
No.
So the question also, if you do that, you get 4 kilowatts, then somebody else, the client who is bringing the work to you, will say to you, well, we don't get 4 kilowatts every time. We don't get capacity for 4 kilowatts every time. We get 1 sometimes, we get 2 sometimes, we get 3 sometimes, we get 5 sometimes, we get 6 sometimes. Because of this standard deviation, what do we do? Where do we take it to? What would you say to them? That's what they get. Not every time, because they're not the one consuming this energy. They're taking it and giving it to somebody else. But the way the order comes is what I've just told you.
Yeah.
So this is a challenge. It's a challenge for decision maker. It's a challenge for everyone. And this is the challenge that is brought about when you have 2 energy mix competing with 1 person, competing with 1 facilities. This is not just a social science problem. This problem is an engineering problem. It's a scientist problem. It's the legal problems, and there are a lot of other issues that goes on with these dynamics, and it has to be solved. And it's our role as a system thinker to try and explain this, because sometimes the decision maker is not able to say, how come we are paying this fine? Can you imagine if we model the fine, if we try and run the model of this fine that the organization will be paying, just look at it. Now, what I want to do was to accumulate the fine every time it goes in. So the accumulations of the fine, this total of net renewable energy, that's what we want to model. That's what we want to look at. We have to change something on top. Is it 3 we had or 5? We had 5 there before, is that correct?
Five.
We see the cumulative amount of money you're going to pay over the 200 days. So this is the debt to the company for not fulfilling their new energy obligation. By the time it gets to the 200 days, that debt has gone to 22.2. So if you are paying 500,000 pounds or 200,000 pounds per kilowatt, if that is built into the service agreement, because what organization we want to do is also, well, I'm happy to give you the contract, but you must meet all my demand. And if you agree to meet those demands, this is what it is. But you can look at exactly, sometimes organizations are willing to go through this, they will pay this price, but whatever they get out of it is much more than what they're getting. So if the amount of money they pay for having this, you can see the money is not even constant, or from time to time we jump up. This is the reality of having not constant variable coming in. And we built all this into the model, and the model is stable, it's working, it's doing what it's supposed to do at the time it was supposed to do it. And if you look at, for example, I want to look at what we did with the model in respect of the order. What do we say about the other comes? Anybody remember what we said about the fossil fuel order? We say once a week. How many is it? How much is it? We said 20 kilowatts every Monday. That's when it comes in. Not correct?
Yes.
Yes. Okay. So if you go here and test either the model is doing what we said it should do. Orders in. So you can see every 7 days. You see the order comes in once a week, and that's what was said earlier on, that if we can have the order coming in once every week. You can see the order is coming in once every week, and that's what it is. I think on this note, I just want to say maybe I should stop sharing now, and then we can have 5 more minutes of deliberation before we stop today. Thank you very much, everyone. Those that I've not seen for some time, I can see some name on the platform. I want to welcome you. I also want to thank the organizers of these sessions and those that have worked with me in GMCO, also putting this together and speaking with each other. So we can put our camera on now and just have general discussions. Where do we go from here?
Yes, Prof.
Okay, Prof. So there's a question in the chat about the equation for the stock and flow diagram. If you can share the equation.
Okay, which of the stock? Which of the stock?
For the old model.
Question is from Shari.
For the old model, Prof.
For the whole model. Well,
Yes.
the equation is there. It's something that has been built, but getting the equations and not having the model, I think the starting point for anyone that is going to use this is to start with the, first and foremost, start with the causal loop diagrams, redraw it, understand it, build a stock and flow diagram, And the next stage is to have an equation for the stock and an equation for the stock and the flow diagram. And for me, I think that is what is important. The equation is not a big deal, but I think the important thing is from our learning process. Can we draw a cost and flow? Can we draw a cost of diagrams in this? Can we draw a stock and flow that? Can we now pick up this? That's where I think that's the way to take it from. Any other questions? We still have about 5 minutes, 4 minutes or so. Any further questions? I could see some faces here. I know some of us are in the UK. I think Abraham is there. Abraham, I'm sure it's in the UK. Ojina, I think I can see some names here. Popular name that we've seen before. I've seen Abdullah here. Abdullah, is that the Abdullah I know very well or the one I don't know?
Yeah, he's the one you know, sir.
He's the one I know, yes. That's Abdullah of Zaria. How are you?
I'm all right. I'm all right.
What are you thinking? So for me, I think one of the things we do is that I did mention the extra division. We, as part of the things we do in terms of our research here, the extra division, it's an organization registered both in Nigeria and the UK, and we provide training and consultancy on